What we are interested in is we are interested in the speed of this plane wave solution versus the speed of this modulating function, because that is something that is going to give us an idea about the nature of the particle's motion. The wave itself may have a certain kind of velocity in a certain direction, and the envelope may be moving forward, backward, or maybe at zero. Hello and welcome back to For the Love of Physics. I am 𝏬🬬🬬🬬 and today we are discussing the concept of the wave packet. The wave packet is a concept in quantum mechanics which is used to describe the dynamics of a particle. You see, in quantum mechanics, when we study the motion of particles like electrons, protons, atoms, molecules, we see that these particles behave like particles, sometimes yes, but they also demonstrate wave-like properties like interference, as we have seen in experiments like Davison-Germer experiment, twin-slit interference experiment, etc. Therefore, there is a great need in the theoretical construction of quantum mechanics to incorporate both the particle aspects and the wave aspects into one entity. And you can say that the wave packet is that entity which embraces both the particle and the wave aspects of microscopic or quantum mechanical particles. And the concept of the wave packet is very simple. It is a wave which is highly localized. It's a wave which is highly localized, and we can construct a wave packet by a superposition of a large number of plane wave solutions. Plane waves that you can see, sinusoidal variations in space that can exist both in the real plane as well as the complex plane, because this wave or wave function is actually a complex mathematical function when we add all of them together in such a manner that they constructively interfere in a very tiny region in space and destructively interfere everywhere else. We end up getting this kind of a localized wave or localized wave packet. Now, what this does is it gives us an approximation as to the presence of the particle in that particular vicinity. So it introduces, number one, the idea that when we talk about a particle in quantum mechanics, then we do not necessarily associate one wave having some standard frequency, amplitude and wave number, but instead a wave packet which can be constructed by the superposition of a large number of waves. Alright, and second of all, it introduces the concept of the particle being found with greater probability in the region in which the wave packet has non-zero amplitude and lesser probability away from that particular region. So if the wave packet represents a particle's motion, then as the particle moves around in space, we should see an evolution of the wave packet through space also. So that is what we are going to study today. We are going to analyze the motion of the wave packet and whether or not the velocities associated with the wave packet can be correlated with physical quantities of the particle like momentum, energy, etc. More specifically, we are going to look at phase velocity, group velocity, how they are different from one another, and how we can derive them from the physical quantities of the particles like energy, momentum, etc. So let me first write down the expression, the mathematical expression for the wave packet. As I said, the wave packet is constructed by a linear superposition of a large number of plane wave solutions. So what is a plane wave? A plane wave is essentially the solution of the Schrodinger's equation for a free particle. I have demonstrated this in my previous lecture, that when we solve the Schrodinger's equation for a free particle, we end up getting a plane wave solution. So you can think of the plane wave solution as simply a sinusoidal variation in both the real plane and the complex plane. So we can write this as e to the power iota kx minus omega t. Alright, so e to the power iota kx minus omega t, where k is the wave number, omega is the angular frequency, and because it is e to the power iota something, I can always decompose this function into sines and cosines in the real and the imaginary plane. So this is basically a very simple plane wave that we are interested in. But because we are doing the superposition of a large number of plane waves, let's suppose every single plane wave is slightly different from one another in terms of its amplitude, in terms of its frequency. So I say the amplitude here is a function of the wave number. And because we are doing a summation, we are adding them up. Let's suppose minus infinity to plus infinity with respect to the wave number k. And I again introduce here a particular mathematical term which is necessary for normalization. This gives us the wave packet as a mathematical function in terms of all the various parameters involved. Alright, so now I want to figure out the velocity of the wave versus the velocity of the packet, the envelope, the modulation that decides where the amplitude is large versus where the amplitude is less. So in a sense, we are going to talk about group velocity and phase velocity. Now, when we talk about a wave, for example, we take a monochromatic light radiation traveling through vacuum, or we take a sound wave, then you must be familiar with this particular expression that if we multiply the frequency with the wavelength, then we end up getting the velocity of that particular wave. So I can simplify this expression by saying that, okay, let's multiply 2 pi here and divide also 2 pi. Okay, then this particular expression basically gives us what is 2 pi nu? It is omega, the angular frequency. And what is lambda upon 2 pi, or we should say what is 2 pi upon lambda? It is a wave number. So I say upon k is equal to velocity. So if we take a wave like a sound wave, or we take a light wave traveling through vacuum, then the velocity of that particular wave is related to wave number and angular frequency in this particular manner. So this is the velocity of the wave, also known as phase velocity. Now, this kind of a relationship is actually true only for those waves which are propagating in what is called a non-dispersive medium. So omega is equal to Vk. Now, so let me just take a side note here in terms of what is non-dispersive and what is dispersive medium. Okay, so let's suppose we have two distinct situations. We have what is called a non-dispersive medium, and we have dispersive medium. What it means is that in a non-dispersive medium, this kind of an expression holds true. What this means is that all waves having different frequencies travel with the same velocity. For example, when we talk about light radiation traveling through vacuum, different frequencies travel at the same speed. When we talk about sound waves traveling through air, different frequencies travel at the same speed. So different frequencies, when they travel at the same speed, then that sort of a medium is called non-dispersive medium. But on the other hand, we have dispersive medium in which frequencies travel at different speeds. Different frequencies travel at different speeds. For example, when we talk about light propagating through a medium in which it is experiencing dispersion, then different frequencies may travel at slightly different speeds. When we talk about deep sea or deep ocean water waves, then they experience dispersion. So essentially different frequencies are traveling at different speeds. In those situations, we do not necessarily find this particular expression, but we may find that omega is related to k as some sort of a function which may depend upon that particular situation. So for non-dispersive case, we have omega is actually a linear function of k. So we have omega is equal to Vk, but for dispersive cases, omega is some function that may depend upon that particular circumstances. So we are going to consider a very general case of dispersive media which transmit waves of different frequencies at different velocities. In that kind of a situation, we can just take omega as a function of k and don't really need to write any specific form of that particular function, because that function may depend on the requirements of the wave packet. So therefore, for a very general case, we are considering omega as a function of k. We don't really know what that function is, but it's some sort of a function depending upon a very general situation of dispersive media. Now, if we want to create this kind of a wave packet, which is essentially the construction of a large number of plane wave solutions, this wave packet is centered around certain values, right? As far as the position is concerned, maybe this is centered around x is equal to 0. As far as the wave number is concerned, maybe it has a high peak or amplitude around k is equal to k0. So what we can do is we can do a Taylor series expansion of this particular function with respect to k0. So if we do a Taylor series expansion of the angular frequency omega with respect to some arbitrary value of k, that is k0, in that situation omega k can be written as omega k0. Let me say that omega at k0 is something like omega naught, okay, plus k minus k0 d omega upon dk at k0 plus higher order terms half k minus k0 square d2 omega upon dk 2 at k0 and on and on. So you must be familiar with these kinds of expansions of functions where you can write down a particular single valued continuous function in this kind of a manner as an infinite series. Now what we are going to do here is that we are going to make an assumption that the wave packet is highly localized. You see, ultimately this sort of a function decides the shape of the wave packet, this sort of a modulation that we see. So for a highly localized wave packet, what we are going to assume is that we are going to assume that the quadratic terms as well as the higher order terms are negligible, okay. So if you make that kind of an assumption that the quadratic terms and the higher order terms can be neglected for an extremely localized wave packet, this expression simply becomes omega k is approximately equal to omega naught, which is the value of the angular frequency at k0. So k0 is some arbitrary wave number at which the wave packet has a certain maxima, plus k minus k0 d omega upon dk at k0. Okay, now what we are going to do is we are going to substitute this particular expression that we have obtained into our mathematical definition of the wave packet and see how we can simplify that particular expression. All right, so let me substitute this expression here in the wave packet expression. Let me rub this here and see what we get. So here we have the wave packet. I have mentioned it as psi as a function of x and t, which is equal to 1 upon root 2 pi from minus infinity to plus infinity phi k e to the power iota kx minus omega t. By the way, we are only dealing with a wave function or a wave packet in the one dimension. So therefore, we have only written kx here. If we substitute omega here from this particular expression, this is simply going to become 1 upon root 2 pi integration minus infinity to plus infinity phi k and e to the power iota, and you have kx minus omega t, right? So omega is within brackets, let me write omega naught plus k minus k naught d omega upon dk times t dk here. Now keep in mind that d omega upon dk is at some value of k naught, okay. So I'm just going to, for the sake of simplicity, write this here, d omega upon dk at particular arbitrary value of the wave number. So if we simplify this further, just let me write all of this down again. So from minus infinity to plus infinity phi k, and here I can write e to the power iota, I can write k minus k naught x. So I've introduced minus k naught x here, and so let me also introduce a plus k naught x minus omega naught t, and then you have minus k naught d omega upon dk t. I hope that this is all clear to you. And let me wrap up the bracket and integration with respect to dk. So now what we can do is we can sort of combine this together, k0 x minus omega t and the rest of the terms together to get something that looks like this. Okay, so if I may rub these parts, okay, let me rub this to create some space. So this can be written as, so this is equal to 1 upon, so let me do one thing. You see here k0 and omega naught. So what is k0? K0 is some arbitrary wave number at which the wave function is sort of at its peak at a given point in time. You see, as the particle is moving, the wave function is, or the wave packet is also evolving, right? So at any given instant in time, the wave packet has a peak corresponding to some wave number and x value. So k0 is that particular wave number. So therefore it is not dependent on time, it's some arbitrary value, and omega naught is simply the value of omega at k0. So this is something that I can take it out of the integration, because this is an integration with respect to k, but k0 is arbitrary, omega naught is also just dependent on k0. So I can take this term out of the integration. So if I take it out of the integration, I simply get e to the power iota k0 x minus omega naught t. So I have taken it out of the integration, and the rest of the terms are 1 upon root 2 pi integration of phi k from minus infinity to plus infinity. You have e to the power iota. So you have k minus k0, and then rest you have x minus d omega by dk, x minus d omega upon dk t, and integration in terms of dk here. I think this is all visible in the camera. So now what we have done is we have essentially separated these terms into two distinct functions if you take a close look. So this is, what is this? E to the power iota k0 x minus omega naught t. This is one plane wave solution, right? And what is this? This is some other function here. So let me just write it separately. So on one hand, we have e to the power iota k0 x minus omega naught t, which is a plane wave solution. And then we have some function here. Let me just say, okay, this is f x, okay, some function, right? So essentially, the wave packet is now written in terms of the product of a plane wave solution and some function. So this is a plane wave solution. And what this function is actually the modulating function. You see, this is the plane wave, but the modulation that determines whether or not the amplitude is 0 somewhere here but non-zero here is decided by this, you can say, envelope or this modulation. So this modulating function is actually fx. What we are interested in is we are interested in the speed of this plane wave solution versus the speed of this modulating function, because that is something that is going to give us an idea about the nature of the particle's motion. Okay, so to do that, let me rub this part of the board once more so that I can create some space. Just take a note of all this. Let me create some space for further calculations. So now I want to compare the speeds or the velocities of the plane wave, that is this particular orange colored wave that you see, versus the modulating function, the envelope, which is also sort of changing with time, right? So if we look at the plane wave that we have here, this is essentially e to the power iota k0 x minus omega naught t, right? If we compare this to some sort of a general plane wave solution, if we make a comparison with some plane wave like e to the power kx minus omega t, How can that be written? Well, quite simply put, well, see, this is a plane wave, right? Moving with some velocity and moving with some amplitude, etc. So this can simply be written as e to the power iota x minus k x minus vt. Yes. So if we make a comparison with this, we essentially find that the velocity is nothing but, if we look at the velocity, what is the velocity? Velocity is nothing but essentially omega upon k, or omega naught upon k. That is the velocity, which is what we have found out, right? Initially, when I was talking about the non-dispersive media, the velocity of a wave was omega upon k, remember? So that is what we have essentially got. This is the velocity of the plane wave, also known as phase velocity. Okay, but because omega naught and k naught are simply arbitrary at a given point in time where the wave packet is, omega naught and k naught is defined, but in general we can write a very simple expression just by writing omega upon k. So let me just write omega upon k. This gives us the phase velocity expression. Okay, the phase velocity is essentially Vp is equal to omega upon k. Now this is the velocity of the wave, the plane wave, the speed at which one particular wave is moving. Now, if we look at the velocity of the modulating function, if you make a comparison of this particular expression, okay, so let's look at the modulating function. The modulating function is 1 upon, so f of x is equal to 1 upon root 2 pi, integration from minus infinity to plus infinity, phi k e to the power iota k minus k naught, and then you see x minus d omega upon dk t, and integrate with respect to k. So if you look at this particular function, this is an integration of a large number of plane waves, right? And if you look at this particular expression, if you make a comparison, let's suppose this is some kind of a constant, x minus vt. Again, if you make a comparison of this particular term with x minus vt, then this v here comes out to be, the velocity here comes out to be d omega upon dk. Again, if you remember when we started the expression, this d omega upon dk is at a particular point k naught. So that simply means that if we measure the velocity of this modulation at some point in time where the wave packet is localized at x is equal to 0 and at k is equal to k naught, but that again is arbitrary, right? So we want a general expression for the wave velocity for all times. That simply comes out from d omega upon dk, and this is known as group velocity. Why is this called group velocity? This is called group velocity because this is not the velocity of one particular wave, but this is the velocity of the entire wave packet. So this is called group velocity, which we can write as Vg is equal to d omega upon dk. Now let's try to understand the difference between these two velocities. What do they actually mean? So let's look at the wave packet here. You see, this is the wave packet. It represents some sort of a probability distribution of the particle. But because the particle is moving with respect to time, the wave packet is also going to move. It's also going to evolve with time. So now if we associate some sort of a velocity of this particular wave, so this plane wave, then this plane wave has a velocity which is the phase velocity omega upon k. Okay, this is the phase velocity. But if we simply look at this modulation, so this modulation is a function that decides where the amplitude is going to be 0, amplitude is going to be non-zero. So you can think of this as an envelope. You have a wave, but on top of the wave you have an envelope which decides that the amplitude is non-zero in a very small region, and that envelope is traveling with time as the particle moves forward. That envelope is a representation of the group velocity. So this envelope, okay, not the specific wave, but this envelope is traveling with the velocity, which is called the group velocity. So you see this, the wave packet is associated with two numbers. One is the velocity of the wave or the wave function, and the velocity of the envelope and how it is traveling through space, that is known as group velocity. Now both these two velocities are not necessarily the same. Let me show you a very simple simulation for this kind of a propagation of a wave packet. So here we have, in the very first case, envelope in which the group velocity and the phase velocity are exactly equal. That means the wave as well as the wave as a group or the envelope is together traveling at the same speed. Now then next we have here a situation in which the group velocity is less than the velocity of the wave. So that means you see the phase velocity is greater, so the wave is traveling at a higher speed forward, but the group is not moving forward in the same speed. And in the third case we have a group which is at rest, but the wave itself is moving forward. So the phase velocity is positive, but the group velocity is 0. Fourth case, we have phase velocity and group velocity are opposite. So the envelope is moving to the left, but the wave is moving to the right. And the fifth case, we have group velocity which is greater than the phase velocity. And in the last case, we have phase velocity which is 0, the wave is not moving, but that envelope, that modulating function is moving. So you can see from these simulations, one thing becomes quite clear, that the phase velocity and the group velocity are not necessarily the same thing. The wave itself may have a certain kind of velocity in a certain direction, and the envelope may be moving forward, backward, or maybe at 0. And we need to understand this quite specifically here, because the phase velocity and the group velocity represent different things. The phase velocity represents the mathematical speed of this mathematical function, also known as the wave function, but the group velocity represents the velocity of the particle, because at the end of the day, the wave packet is a representation of the motion of the particle. So as a particle is moving forward, this group, this wave packet, this envelope is also moving forward with the same speed. So let me demonstrate that to you. Okay, so let me rub all of this again. I hope you have noted this down. Let me rub this first. So essentially what happens is that when we have a superposition of a large number of plane wave solutions in such a manner that we end up getting a wave packet, in which the wave packet has a non-zero amplitude in a very tiny region and a zero amplitude everywhere else, then the velocity of that wave packet as the particle moves forward is given by the velocity of the group of waves, also known as group velocity. And the individual velocity of the wave itself may be different. It could be phase velocity. Now I want to understand what is the relationship between group velocity, phase velocity, and the parameters which define the particle's physical quantities. All right. So let me write down what we have already obtained. We have obtained that phase velocity is equal to omega upon k and group velocity is equal to d omega upon dk. Now let us invoke some of our earlier known expressions. So let us look at the Planck postulate. So if you look at the Planck postulate, E equals h nu, this can be written as E equals h upon 2 pi times 2 pi nu. So this can be written as h cut omega. So if I differentiate it, all right, h cut is a constant. So the only thing I can do here is dE is equal to h cut d omega. So I've taken a differential here. And if I take the de Broglie hypothesis, which is P is equal to h upon lambda, or lambda is equal to h upon P, this can be further written as h upon 2 pi times lambda. So this is equal to h cut times, what is 2 pi upon lambda? wave number k. So h cut is a constant. So if I take differential, this becomes dp is equal to h cut dk. So I'm just giving you a very simple derivation of the expressions that I'm going to obtain. So let's say this is point number A, and let's say this is point number B. So if I use point A and point B, we can show that the group velocity of the waves is related to the particle's energy and momentum in such a manner that Vg is equal to d omega upon dk, which can be written as d omega. So I multiply with h cut d omega, and then in a denominator h cut dk. Okay, we have a dk here. So what is h cut d omega? It is this. And what is h cut dk? It is this. So this is actually equal to dE upon dP. So this basically gives me an idea about the velocity of the particles wave packet in terms of the energy and the momentum of the particle. So we can show that the group velocity is equal to d omega upon dk in terms of the physical quantities of the wave, and in terms of the physical quantities of the particle, it's dE upon dP. So quite simply, this is the expression that we have obtained. Now what about the phase velocity? We can obtain the phase velocity also. The phase velocity simply comes out to be, if I just use Vp is equal to omega upon k and multiply with h cut above and below, this gives us h cut omega is E upon P. Okay, so this is the phase velocity. Now we need to look at a couple of things here. Let me first write this down. This is equal to omega upon k is equal to E upon P. So essentially what we have done is we have derived these expressions in terms of the wave quantities, physical quantities of the wave, and also in terms of the physical quantities of the particle, because ultimately the wave packet is a representation of the particle's motion. So this is the wave packet. Wave has a certain kind of a speed, and the particle or the modulation has a certain kind of a speed. Now it must be kind of obvious now that the group velocity of the wave packet should be the same as the particle's velocity. When we think in classical mechanics, we think of a particle moving, right? Displacing distances over periods of time. So the velocity of the wave packet, the group velocity, should be equal to the particle's velocity. So let us demonstrate that. Okay, to demonstrate that, let us take a very general sort of a relativistic case, okay, or a relativistic particle. So in a relativistic particle, we know that the energy of a relativistic particle is given by m0 square c to the power 4 plus p square c square. I think you guys are familiar with these expressions if you have studied relativity. So we can further simplify that as E square is equal to m0 square c to the power 4 plus p square c square, where m0 is the rest mass of the particle, c is speed of light, p is the relativistic momentum, and E is the total energy. Again, if we take a differential on both these two sides, we can write this as 2E dE is equal to m0 and c, they are constants for a given particle, this is 0 plus 2p dp c square. Again, let us simplify this further. Okay, so what we have here, 2E dE, again I can bring 2p dp, and this is equal to c square. So 2 and 2 gets cancelled, of course. Now what is dE upon dP? It is simply the group velocity. So then this simply becomes what? dE upon dP is equal to c square p upon E, where p is the relativistic momentum and E is the relativistic energy. Now we need some more space to write this further. Can I rub this? Okay, let me rub this part of the board to elaborate further. Okay, so let me rub this. So now this can be further simplified as, we can write this as dE upon dP, which is, by the way, the group velocity, right? dE upon dP is the group velocity of the wave, of the group of waves, and this is, on the other hand, the phase velocity, which is basically the wave of, or the velocity of a plane wave. Okay, so for the particle, we have dE upon dP, which is equal to c square. Okay, now we have the relativistic momentum. What is momentum? Momentum is essentially mass times speed, but the relativistic momentum is gamma m0 v. So m0 is a rest mass, gamma is a gamma factor. So gamma factor is what? Gamma factor is equal to 1 upon root over 1 minus v square upon c square. And again, what is the energy? Energy can be written in various forms. And one expression for energy is this. Another expression for energy is gamma m0 c square. Okay, m0 is a rest mass. This is the gamma factor. So if we write this down, we end up cancelling gamma and m0 in the numerator and the denominator. C square also gets cancelled. So finally, we have this particular expression. So the group velocity, because this is ultimately the group velocity of the wave packet, Vg is equal to dE upon dP is equal to what? Just V. What is V? V is just the velocity of the particle. Vg is the group velocity of the wave packet and V is the velocity of the particle. It simply means that the particle is traveling at the group velocity of the wave packet, which kind of makes sense, right? Because ultimately in quantum mechanics, the wave packet is supposed to be an approximation to study the dynamics of the particle. So the wave packet is moving forward as an approximation for the particle moving forward. So this kind of bridges the gap between classical physics and quantum mechanics, that in classical physics we have a point mass particle which is moving forward with a certain velocity, but the quantum mechanical picture is that the wave packet is moving forward with the same exact velocity, or the velocity of the group of waves is exactly the same as the velocity of the individual particle. So you can think of the wave packet's center to be tracing out the same trajectory as that of the classical particle. Keep in mind, however, that we are only talking about the physical significance of the group velocity, which is the same as the velocity of the particle. However, if we look deeply, what about the phase velocity? Well, this doesn't necessarily have any correlation with physical sort of a quantity. Let me demonstrate that to you by taking a couple of examples. So if we take the example of, let's suppose, light, okay, you know, light traveling in vacuum, okay, let's suppose there's a electromagnetic radiation, light photon traveling through vacuum, then what is the phase velocity of light photon? The phase velocity is omega upon k. Right, we say omega upon k, or in terms of the photon, we can say E upon P. Okay, but what is the momentum of a light photon? So you must be familiar with the momentum of a light photon is written as E upon C. Okay, so this can be written as numerator E. The momentum is E upon C. So E and E gets cancelled, C comes to the numerator, you end up getting C. So the phase velocity of a light photon is same as the speed of light. But what about the group velocity? If you look at the group velocity is equal to dE upon dP, right? So what is dE? Let me just keep dE as the same. But what is dP? Because P is equal to E upon C, C is a constant. So dP is equal to 1 upon C dE. Again, what we end up getting is C. So the phase velocity of a light photon is the speed of light, and the group velocity of a light photon is the speed of light. We are talking about light traveling in a vacuum. However, if we are talking about a particle, let's suppose, like a relativistic particle traveling, out there in space, then what happens? If we talk about a relativistic particle, then the group velocity is of course equal to the velocity of the particle, but what about the phase velocity? So if we look at the phase velocity, Vp is equal to E upon P, right? Where E is the relativistic energy gamma factor m0 c square, and p is a relativistic momentum gamma m0 v. Okay, so again these two terms gets cancelled and we end up getting c square upon v. What is v? V is the velocity of the particle, which we have demonstrated that is nothing but the velocity of the wave packet. So therefore we can combine the velocity of the wave packet with Vp and say that Vp Vg is equal to c square. Please notice this particular expression. The v, velocity of the particle or the wave packet, times phase velocity is equal to c square. What does this mean? That the product of the phase velocity and the group velocity is equal to c square. It means that because the particle can never really travel at the speed of light, because we know from special theory of relativity that any particle that has some kind of a rest mass can never really reach the speed barrier, which is the speed of light. Because of that reason, the phase velocity is always greater than the speed of light. You see, the group velocity is always less than the speed of light. And because of that reason, the phase velocity is greater than the speed of light. I want you to notice this because we know that particles cannot really travel beyond the speed of light. That is a limitation which is put on particles having rest mass by special theory of relativity. But what does this mean then? The phase velocity greater than the speed of light? Well, we have to understand that the phase velocity doesn't really represent anything physical. Okay, when we are talking about quantum mechanics and the concept of the wave packet, we must always remember at the end of the day, the wave packet is a mathematical function. I have used the word wave function previously. So it's a wave function, and the wave function is a complex function which is a solution of the Schrodinger's equation, right? And here when we are talking about the velocity of the plane waves, we are essentially talking about the velocity of these wave function solutions, and they are ultimately mathematical, as we can never really measure them, as we can never really see them. We only know the particle. We only know the particle's velocity, which is the group velocity, but we can never really measure the wave associated with it. It is a construct that is created in mathematics to create a satisfactory theory that can best approximate or predict how quantum mechanical systems are going to evolve. So the phase velocity doesn't really have any corollary with the particles' physical quantities. It is only the group velocity which is the particle's actual velocity as it traces a particular trajectory in space. In certain situations, the phase velocity is equal to the group velocity. This is the case of non-dispersive medium examples. And in certain situations, when we are talking about dispersion, then the group velocity and phase velocity are not equal. The group velocity could be greater, equal, or less than the phase velocity depending upon the circumstances. So that is all in terms of group velocity and the phase velocity of the particle's wave packet as we study the concept of wave packets in quantum mechanics. In the coming lectures, we are going to talk about how this concept of a wave packet introduces the probabilistic interpretations of the particle's existence. Alright, how is it that we end up with something called the Heisenberg's uncertainty principle, which is one of the foundational pillars of quantum mechanics? Well, it arises as a natural consequence of the concept of this kind of a wave packet idea. So we'll discuss that in the next class. That is all for today. Thank you very much. Have a nice day. Bye-bye. Take care.